Yesterday we have started to learn parabola. So now we shall continue with parabola. Now we know that parabola is given by its canonic equation. Y squared is equal to 2 times p times x, where p is positive. And if we draw this parabola, it looks like the following. It has one branch, it has a vertex at the origin, it has one focus, and it has one directrix. The distance from focus to the vertex, OF, is equal to P over 2. So we should divide this parameter by 2, and it will be this distance. And again, the distance from the vertex to a directrix is also P over 2. So OP is equal to P small over 2. Looking at this picture and remembering the property of parabola, or its definition, that if we take any point M, then the distance from M to F is equal to the distance from M to the directrix. It is expressed by the formula MF is equal to MIH. We conclude that the eccentricity of a parabola is equal to 1. So we can draw the line of eccentricities. Here the value is 0. If the eccentricity is equal to 0, then the line is a circle. In the case of an ellipse, the eccentricity belongs to the interval from 0 to 1. And if the eccentricity is greater than 0, and until the infinity, these values of eccentricity correspond to hyperbolas. And exactly one point where the eccentricity is equal to 1 corresponds to parabola. So here we also should write parabolas, since there are various sorts of parabolas which depend on parameter p, and all of them have the eccentricity which is equal to 1. The next item is the focal property of parabola. Focal property of parabola. Again, assume that our parabola is made of some material, of some light reflecting material, and assume that at the point of its focus we place some source of light. Then we can consider the line Fm as a ray of light. This ray will reflect from the parabola and will go to infinity. And it turns out that this reflected line will be parallel to the axis of our parabola. And our goal is to show that it is correct. In order to prove this fact, we need to derive the equation of a tangent line, because the reflection law is written with respect to the tangent line. So if we draw here the tangent line, and if we take the perpendicular to this tangent line, then this angle should be equal to this angle. The incident ray and the outgoing ray, reflected ray, form the same angle what's perpendicular to the tangent line to our parabola. Therefore, let's derive the equation of tangent line to parabola. Assume that our point M had the coordinates x0 and y0. Then, because it is on the parabola, we can write that y0 squared is equal to 2 times p times x0. And assume that we have some point on the tangent line. For example, this is point B with the coordinates x and y. And we should write the equation that will comprise x and y and x sub 0 and y sub 0. Again, write the equation of a tangent line to a graph of some function. Y minus y0 is equal to f prime of x0 multiplied by x minus x0. This is the equation for the tangent line to a graph of the function y equals to f of x. And in order to write this equation, we need the formula for the derivative. Let's take the equation of our parabola. Y squared is equal to 2 times p times x. And let's substitute y equals to f of x to this equation. As a result, we get f of x squared is equal to 2 times p times x. We need the derivative. We need to set the prime sign, which means that taking the derivative of the function. So let's surround our expression with brackets and set the derivative sign. we set the prime. And similarly in the right hand side, we set the prime. According to the rules for calculating derivatives, if we have a square of function, then the derivative of such a square will be 2 times f of x times f prime of x. And in the right hand side, we should take the derivative, we should differentiate the product of two constants with a variable x. Because the number 2 and p are constants, they are written, they are unchanged. And the derivative of x is equal to 1. Therefore, we get 2 times p, because x prime is equal to 1. Thus, looking at this formula, we can express f prime through f and p. The coefficient 2 can be cancelled because it is present in the left hand side and in the right hand side of our equality. As a result, we get f prime of x is equal to p over f of x. But f of x is equal to y. Therefore, we get that f prime of x is equal to p divided by y. In this formula, we need the derivative at the point x, which is equal to x sub 0. Therefore, we need to substitute here the value x sub 0 in place of x, and here also. And therefore, because y sub 0 is f of x sub 0, we derive that f prime of x sub 0 is equal to p over y sub 0. Thus, we have the required value of the derivative in order to substitute to this equality. Let's perform such a substitution. Y minus y sub 0 is equal to p over y sub 0 multiplied by x minus x sub 0. In order to remove this denominator, let's multiply both sides of this equality by this denominator. As a result, we get y sub 0, y minus y sub 0 is equal to p times x minus x sub 0. Now let's expand both sides of this equality. We get y sub 0 multiplied by y minus y sub 0 squared is equal to 2px minus, not, just px minus px sub 0. Now let's recall that the point with the coordinates x sub 0, y sub 0 belong to the parabola. Therefore, this equality is fulfilled. For this purpose, for this reason, we can replace y sub 0 squared by the following expression. So, y sub 0 squared is equal to 2 times p times x sub 0. Therefore, we can write y sub 0 multiplied by y minus 2px sub 0 is equal to px minus px sub 0. Now we can move this term, which is with minus, from the left hand side of this equality to the right hand side of this equality. and the resulting expression, the resulting equation will be y times y sub 0 is equal to px plus p x0. The equation is rather simple and it cannot be simplified anymore. Therefore, this is an ultimate equation for the tangent line of a parabola. So, the equation of a tangent line to parabola is written here in the box. So now we can use this equality. I shall copy this equality to here in order to preserve it. And then I wipe our calculations in order to make some empty space. We declare the focal property of parabola. Let's write the statement of this focal property. First of all, we shall write the statement in terms of rays of light, so in terms of optics. And then we convert the statement to the statement in terms of geometry. Well, the focal property of parabola. Any ray of light emitted from the focus of a parabola upon reflecting from it, goes to infinity, goes to infinity, parallel to the axis of this parabola. Any ray of light emitted from the focus of a parabola, upon reflecting from it, goes to infinity parallel to the axis of this parabola. Just like in our picture. So, rays emitted from the focus goes here. At the point M, it reflects from our parabola, and then it goes to infinity. And this line is parallel to this line, which is the axis of our parabola. Now let's draw a picture in such a way in order to reformulate this statement in terms of geometry. From the quality of the angles phi 1 and phi 2, we conclude that the complementary angles alpha 1 and alpha 2 are also equal to each other. Because alpha 1 is 90 degrees minus phi 1 and alpha 2 is equal to 90 degrees minus phi 2. And now let's extend our tangent line until it crosses the axis of our parabola. And let's denote this crossing point through N. Because the focal property in terms of optics declares that this line and this line are parallel, we can continue these two lines, the reflected ray, and we see that our tangent line crosses two parallel lines. But from the elementary geometry we know that if a line crosses two parallel lines, then it forms the same angle with each of these two parallel lines. This angle alpha 2 is equal to this angle alpha 2. But this angle alpha 2 is equal to the angle alpha 1. So if we consider the triangle, F M N, in this triangle, two angles are equal to each other. This one and this one. Alpha 2, and this is also alpha 2. But if in the triangle two angles are equal to each other, then the opposite sides of this triangle are also equal to each other. So from alpha 2 equal to alpha 2, we derive that the distance MF is equal to the distance NF. This means that the triangle NFM is equilateral. second statement of the focal property of parabola. For any point M on a parabola, for any point M on this parabola, the triangle formed by the focus F of this parabola by the point M and by the crossing point of the tangent line at M with the axis of this parabola is equilateral. Which means MF is equal to NF. Well, here let me denote this crossing point. So this is the point N. Proof of focal property of parabola. Since in the geometric statement of the focal property we have the point N, let's find its coordinate. The point N is on the axis of parabola, and the axis of parabola is the horizontal axis of our coordinate system. And the vertical axis goes through the vertex of our parabola, and it is perpendicular to the horizontal axis. So let's find the coordinate of N. Since it is placed on the horizontal axis of our coordinate system, its second coordinate, the y coordinate of N, is equal to 0. Y is equal to 0. And we should substitute this value into our equation of the tangent line. As a result, we find that the left-hand side of this equation vanishes, and we find that 0 is equal to px minus, oh, I'm sorry, here the plus sign should be here, not minus, but plus. And we find that px with x sub 0 is equal to 0. And as a result, we find that x is equal to minus x0. So, the coordinate of the point n is equal to minus x0 and 0. Then our goal is to prove that Fn is equal to Fm. Let's calculate the value, the distance from F to N. The distance Fn is composed of two parts. This part and this part. Here, this point is the origin, and this distance from the origin to the focus is equal to p over 2. The distance FO is equal to p over 2. And the distance ON, indeed, the coordinate of the origin is 0, while the coordinate of the point N is minus x0. Therefore, the distance from this point to this point is equal to x0. And then, substituting this value and this value to our formula, we'll find that the distance Fn is equal to p over 2 plus x0. Now let's proceed to the distance Fm. Initially, for this distance, we have the formula with the square root. X minus p over 2 squared plus y squared, where here x sub 0 and y sub 0. However, we know that Fm is equal to mh. What is mh? If I draw the directrix, then mh is the distance from M to the directrix. And the distance mh is also composed of two parts. This distance and this distance. The distance from M to the coordinate axis is equal to the x coordinate of M. So let's denote this point for example through Q. MH is equal to MQ plus UH, where MQ is equal to x sub 0 and QH is equal to P over 2, because the distance from the vertex to the directrix is equal to the distance from the vertex to focus, and this distance is equal to P over 2. Therefore, if we substitute these values into the formula for MH, we find that MH is equal to P over 2 plus x0. Now, The rest is to compare this formula and this formula. As we see, these two formulas are equal to each other. Therefore, from this one and this one, we conclude that Fn is equal to Fm. And thus, we have proved the required equality, thus the proof is over. We have completed the topic about parabola, and finally I want to describe you the practical application of this focal property of parabola. If you take some part of parabola and rotate it about its axis, you get something like parabolic surface. And if you take some source of light at the focus of this parabolic surface, then each ray reflected from this surface will go parallel to the axis of our parabolic surface. As a result, we get the parallel flux of light. Such a device, or such a surface shaped like a parabola, is used in telescopes, in parabolic antennas, and in car lights, in train lights, and also in ship lights. So, such a focal property of a parabola is rather useful in practice. Thus, now we have completed learning ellipse, hyperbola and parabola separately. Our next step is to study them all together as curves of second order.